everybody, Thrasher here. We learned about gravitational potential energy, this energy associated with the work done by the force of gravity for here on Earth. But now that we're learning about a more universal force of gravity, it stands to reason that we should revisit that gravitational potential energy. That's the plan in this video. Before we actually get started with that, I do want to go over just a couple of quick reminders. This right here, this was that original equation for gravitational potential energy. It's based on the mass of the object, the gravitational constant, 9.8 here on Earth, and h, how high up you are. Okay? Gravitational potential was about those heights and whether or not you were decreasing in height or increasing in height. Also, team, this almost maybe is a little silly, but let's remember the idea of a number line, because maybe surprisingly, this is going to be important. Okay? Of course, you're all familiar with the idea that larger positive numbers are more, we would say, than a smaller positive number. Like positive 8 is more than 3. If I'm going to the right, 3, 4, 7, 9, 10, I'm increasing. Then if I'm going to the left, of course, I'm decreasing. 8, 7, 6, I'm getting smaller and smaller and smaller. Left is decreasing. Team, that's still true once we enter the negative realm. Negative numbers, we say, are decreasing as we go to the left. Negative 10 is a smaller number than negative 9. Okay, I know that just magnitude, the number 1, 0, that seems like it's more than 9. But again, if I'm decreasing, if I'm getting more and more negative, that's also getting smaller. Okay, that's going to come into play right now. When we were first learning about gravitational potential energy and we were using this equation for height, if you recall, we had to choose a 0 spot. And often, team, because it was easy, we would say right there is 0. But to be honest, we didn't have to choose this spot here as our h equals 0 location. In fact, often I would have students say something like, well, Mr. Thrasher, could you have the 0 spot since you get to choose at the top, maybe where the ceiling is? Is that possible? Yeah, it's definitely possible. Let's just quickly analyze that and see how that works out. It's still the same. Now, that means that if I'm holding like a red ball, that's what this image is showing. Well, that means in the beginning, I have some negative starting height. That's what it looks like here in my picture. This object here is starting with some negative h. So if I was to write out the equation for gravitational potential energy, I have UG equals mgh. I would be plugging in, I know I don't have any actual numbers here, I'd be plugging in a negative value, which is a little different. But team, here's the most important part. Let's think about if I dropped this ball, as it moved downward, down and down and down and down, I tried to change colors, it's not letting me. As I move downward, well, notice I'd be getting more and more and more negative. This is more negative the further down I go. Remember that number line? If I'm getting more negative, UG, while it's weird, is still getting smaller. And that's good because that's what we had before. When we were using positive values as gravitational or objects falling, as it went down, the gravitational potential got smaller. So it's weird choosing up here as 0. It's weird maybe having a negative, but it still matches. As that object's falling down, it's gaining kinetic. UG is getting more and more negative, so the value of UG is getting smaller, which we expect. The gravitational potential decreases, the kinetic energy decreases. Okay? I think I said that right. Well, team, now let's zoom out. Let's think of our more universal force of gravity. And let's again derive the equation for gravitational potential energy. If you forgot, the way we got it was by looking at the work that was done. If I'm going to look at the work done by the gravitational force in our universal level, well, that's going to be equal to G m1, m2 divided by r. And notice, here I have an example. Let's say I have, I don't know, a planet next to a star, or maybe it's a moon next to a planet, whatever. There's a gravitational force between them based on g mm r squared. Now, the work is the force multiplied by the displacement. If this object was just free falling straight towards colliding, well, the distance it's traveling is in that same direction as the force. Remember, the force of gravity is between two objects. So it is, in fact, the same r that I have here. So let's simplify that. I have an r. This is in the numerator. Here I have r squared in the denominator. I'm going to get rid of one of those exponents. The gravitational potential energy in a universal scale is g m1 m2 divided by the radius. That's our gravitational potential energy. Now, team, this is where the video gets weird. Because R, again, we need to decide where we're going to measure that from. And where would we do that? Like, before, everything had to do with like us on Earth. So it makes sense to use like the surface of the Earth because everything was, near that. It was our reference frame. But now I might be talking about the Earth. So should I still use the surface? Should I use the center of the Earth? What about if these are two totally different astronomical objects? Would I still use the Earth as my measuring point? Of course, the Earth orbits things. Its distance is changing. That would be weird. So team, physicists use a different way to measure, a different reference point. And that's when this thing is going to get a little strange, okay? Where should we choose our zero distance to be? Physicists, by convention, choose R to be a spot infinitely far away. That's weird. Infinitely far away. Way out over here if it helps. Or way down here. It doesn't really matter. It's some spot that's an infinite distance. And that leads us to some certain repercussions, so to speak. Okay? I'm going to delete this box right here and we'll talk through it. Okay. By convention, we're going to choose R to be a spot super far away. That is akin, if you remember the example on the past slide, where I had the ceiling be our 0 point. So before we had the height as like 0 at the ceiling and then it made our values negative, it's the same kind of idea. If the spot that we're choosing is infinitely far away, well, that means when these two things, or maybe when this object here is moving towards this way, it's going in the opposite direction, it's negative. We're going to have negative values. And team, just like before, that's actually okay. Because if this planet is getting more and more negative, if the gravitational potential energy is getting more and more negative, that means UG is decreasing. And that still makes sense, because if it's increasing in its velocity as it's approaching right before collision, kinetic energy goes up. By conservation of energy, UG should be going down. All this is to say, team, now when we see this equation for gravitational potential energy, there is a negative value here, okay? But it doesn't change anything that we learned about before for this idea of gravitational potential energy. It's also worth noting, team, that really when we're talking about gravitational potential energy, we're caring about the change from one spot to another spot, okay? If this planet was here and then here, that change in radius, whatever, I know it's measured from infinity, but still looking at a change that's getting a smaller amount. Oh, okay, well, a smaller denominator here would be a bigger overall number, but it's negative. So it's a bigger negative, so it's a smaller gravitational potential. Or let's say this was happening the other way. Let's say somehow by some large force of the universe, I was moving this outwards. So now this distance between them, the change in distance would be increasing. So the denominator is going to get big. That makes the whole UG get small. Oh, except it's a negative value. Oh, that means the gravitational potential energy is getting less negative, it's getting large. Oh, it's a bit of a mind twist, a mind melt, but it does still make sense. Nothing is changing. When things are getting closer, their gravitational potential energy is going down, probably their kinetics going up, and vice versa, okay? Also, team, for the College Board exam, for this weird kind of negative gravitational potential energy, they often will have a graph associated with it. And let's think about this graph. Okay, if we have a certain given object, and of course G is a constant, we have this relationship that the gravitational potential energy is related to negative 1 over R. That's this shape right here. My head is in the way, but I have this graph curving like this. That's a representation of negative 1 over X. Y is related to negative 1 over X. Gives you a graph that looks kind of like this. You might see this graph on the College Board exam. To be honest, team, again, what is it telling us? It means that if two things are increasing in their distance apart, their gravitational potential energy is getting smaller. Okay, it's approaching 0. If their distance is getting closer and closer and closer, okay, their gravitational potential energy is decreasing. Okay, it's getting more and more and more negative. It's going down. It's weird at first. It's, again, a bit of a mind twist. Okay, but this graph has been known to show up. Last main bit, team, and then we're done with this video. Okay, when we're doing conservation of energy, we used to say, okay, E naught is equal to E. So K plus UG equals, I mean, it's some constant value, right? I could write constant. But now, in the universal scale, in more large-scale things, you will expect to have negative gravitational potential energy. So seeing it like this is pretty common. Or, if I just kind of pull out that negative, K minus UG is a constant. You might be told in problems that gravitational potential energy is a negative quantity. And that's, again, following this convention. Or now when you do conservation of energy, before we were always just adding things, but now you might be subtracting or you're adding in that negative value. It's strange. But again, team, I'm going to end on this slide, okay? The key takeaway, nothing about the concept has changed, okay? When things are far apart from each other, they have more gravitational potential energy. As that distance between them gets smaller and smaller, that gravitational potential goes down. And that should make sense because let's imagine they're falling towards each other under the influence of gravity, accelerating towards each other. They're speeding up, so kinetic energy is going up. So if energy is conserved, that almost certainly means that the gravitational potential energy is going down. So I know there's a weird negative sign now, but again, that doesn't change anything about our concepts of gravitational potential energy. Okay? Oh man, a weird video, I know. To be honest, team, I might have a link in the description for another video or two on YouTube that I like. Okay? So if you're still confused, it might be worth it to check out those other videos. But that's it. I'm going to sign off now. Thanks a lot for watching.